Today I'm going to start my presentation of Euclid Book 10, which is comprised of 115 propositions and 4 definitions. Now you would think that 4 definitions would be easy, right? Guess again. Alright. Let's get into this, shall we? Euclid Book 10, definition number 1. The magnitudes are said to be commensurable, which are measured by the same measure, and those incommensurable, which cannot have any common measure. Now, what does that mean? Okay. The numbers 4 and 8 are commensurable. Why is that? Because 2 can measure 4, and 2 can measure 8. That's what it means. Now, what about the numbers 8 and 9? Is there any number out there that can measure both 8 and 9? You say, well, the number 1 can. Here's the problem. In Euclid's Elements, number 1 is considered a unit, not a number. So we drop number 1. Is there any other number that can measure both 8 and 9? According to Euclid, the answer is no. There you go. You say, well, you can measure them with a remainder. No. Remember, this had to measure it out without a remainder. That's how Euclid worked. Okay, so, having said all that, now you know. Number 2. Straight lines are commensurable in square when the squares on them are measured by the same area, and incommensurable in square when the squares on them cannot possibly have any area as a common measure. Now, what does that mean? Okay. Now we go with Mr. Illustration. Okay. We have 2 square, which is 4, 4 square, which is 16, and 8 square, which is 64. Now 2 can measure 4, and 2 can measure 8. 4 can measure 16, and 4 can measure 64. So this square area here can measure this square area, and this square area here can measure this square area. That's what he's talking about. Those are commensurable. Now, what about up here? We have 5 square, which is 25, and 7 square, which is 49. Obviously, there is no number that can measure both 5 and 7. And there is no number that can measure both 25 and 49. Not even a square number. There is no square number that can measure 25 and 49. That's incommensurable in square. That's what they're talking about. Okay. Now the difficult one comes with number 3. This is Euclid Book 10, definition number 3. With these hypotheses, it is proved that there exist straight lines, infinite in multitude, which are commensurable and incommensurable respectively. Some in length only. So that means that you could actually have a number which, say, it's just like, here, we got the numbers 2, 4, and 8. You could actually have a number, and I tried all day to come up with a number on this, but I couldn't do it. So, if you want to experiment and try, that's fine. What the way this is going to work is 2 can measure 4 and 2 can measure 8, but if you had commensurable in line or in length, but not commensurable in square, what you would have is like the numbers 2, 4, and 8, but their squares could not measure each other. Well, this square couldn't measure this or this. That's what it's trying to say. So basically you would say A can measure B, A can measure C, but D cannot measure E and D cannot measure F. That's what it's saying. Okay? Okay? Alright. Some in length only, and others in square also. Now, what does it mean by others in square also? Well, just like this. 2 can measure 4, 2 can measure 8. Of course, 4 can measure 16, and 4 can measure 64. So, the lines themselves can be measured by something, and the squares can also be measured by a square area. So that's what that means. Okay. Let then the assigned straight line be called rational, and those straight lines which are commensurable with it, whether in length and in square or in square only, rational. Now, what that means is that this line right here would be called rational because it measures both this and this. That's what it's saying. All right? Now, what if you had a line that did not measure either one of these, but if you squared that and squared the other two, it would? That would also be called rational. Now, how did they come up with this? Okay. First, they drew a perfect square like this. So all four of these sides are equal. All right? All four of them are equal in length. Now, what they said was, we're going to go by Euclid Book 1, proposition number 47, which is called the Pythagorean theorem. The Pythagoreans came up with it first. Euclid used it as a proof in Euclid Book 1, proposition number 47. Okay? So a squared plus a squared equals b squared. All right? So what he said was that you could actually come up with a length b squared, that a squared well, b wouldn't be able to be measured by a, but b squared would be able to be measured by a squared. And that's what he's saying. So b can't be divided by a, but b squared can be divided by a squared, and that's what he was saying. Okay. But those which are incommensurable are irrational. Okay, so that means that if the line can't measure the other line and the line square can't measure the other line square, then those numbers are incommensurable. Okay. And let the square on the assigned straight line be called rational, and those areas which are commensurable with it rational, but those which are incommensurable with it irrational, and the straight lines which produce them irrational. That is, in the case the areas are squares, the sides themselves, but in case they are any other rectilineal figures, the straight line on which they are described squares equal to them. Now, if you didn't understand that, don't worry, I didn't either. But those are the 4 definitions of Euclid Book 10. Now we can proceed on with the 115 propositions. And yes, some of them not necessarily will be 3D, but they will lead into 3D. And you'll see that in my future proofs. Alright, I hope you had fun with these definitions. The proofs are just as hard. Okay, we're going to have fun with this. I'm going to tell you more in a future video. Stay tuned.